Fundamental Theorem of Calculus, Part 2. We're going to start by looking at the Fundamental Theorem of Calculus, Part 2. So recall that if big F prime of x is equal to little f of x, the indefinite integral of little f of x is given by the integral of little f of x dx is equal to big F prime of x plus c. So the way I like to think about this is, well, little f of x is big F prime of x dx. So when I take the integral of f prime of x, then that gets me to the original function f of x plus c because we have an indefinite integral. So the Fundamental Theorem of Calculus Part 2 says assume that f of x is continuous on the closed interval from a to b, and once again we have that relationship that big F prime of x is equal to little f of x on the closed interval from a to b. Then, now, we're solving the definite integral. The definite integral from a to b of f of x dx is equal to the antiderivative big F of b minus big F of a. Or this is another way to write it, the antiderivative f of x from a to b. So the additional step I'll write here to kind of help make the connection is that if I have the integral from a to b of big F prime of x, since we're saying that f of x and big F prime of x are interchangeable, right? That's part of the hypothesis. So the integral from a to b of big F prime is equal to the antiderivative of big F prime evaluated at b and then minus evaluated at a. So informally, the Fundamental Theorem of Calculus Part 2 says we can evaluate a definite integral by solving for the antiderivative, big F of x, substituting in the limits of integration b and then a, and subtracting. So notice there is no constant when evaluating a definite integral because the answer is a number. That number represents the area under the curve f of x from a to b. So this Fundamental Theorem of Calculus is a tool for finding the exact area under the curve using the notion of antiderivatives. Alright, let's jump into an example. So the integral from 1 to 3 of x squared dx. Now previously, this is a definite integral. We could approximate using rectangles, or we could use the limit definition of a definite integral to find the exact area under the curve using the limit of Riemann sums. But now we have the Fundamental Theorem of Calculus, which says that I can look at the function x squared and take its antiderivative. So the antiderivative of x squared is x cubed over 3, and evaluate this on the interval from 1 to 3. So I'm going to substitute in 3 first. The upper limit of integration goes in first. So I have 3 cubed over 3 minus, I substitute in the lower limit of integration, 1 cubed over 3. So I have 27 over 3 minus 1 over 3, or 26 over 3. So the exact area under the curve is 26 over 3. We didn't need an approximation and we didn't need to use the limit of the Riemann sums definition as long as we can find the antiderivative, the general antiderivative of x squared. In this example, the integral from 0 to pi over 4 of secant squared x dx. The antiderivative of secant squared is tangent x, evaluated from 0 to pi over 4. So notice I did drop the integral sign because I've taken the antiderivative, and now I substitute in pi over 4 minus tangent of 0, and tangent of pi over 4 is 1, tangent of 0 is 0, so my final answer is 1. Here we have the integral from 1 to 4 of 3 radical x plus 2x dx. So we have to take the antiderivative of 3 radical x plus 2x, or 3x to the 1/2 plus 2x. So the antiderivative here, so I'm going to end up with 3x to the 3/2 times 2/3, and then plus 2x squared over 2 and this is all evaluated from 1 to 4. So the 3's are going to go ahead and cancel here, and I end up with 2x to the 3/2 plus x squared from 1 to 4. And I go ahead and substitute in 4 into each x, into the entire antiderivative. So 2 and then 4 to the 3/2 plus 4 squared. So all of that minus, substituting in 1, 2 times 1 to the 3/2 plus 1 squared. So here we have 4 to the 3/2, that's the square root of 4, which is 2. 2 cubed is 8. So inside of here I have 2 times 8, that's 16, plus 16, minus here I just have 2 plus 1. So I have 32 minus 3 for an answer of 29. Here I have the integral from 0 to 2 of e to the 2x dx. So the antiderivative of e to the 2x is 1/2 e to the 2x, evaluated from 0 to 2. So we substitute in 2 first, so 1/2 e to the 2 times 2 minus 1/2 e to the 2 times 0. Well, that just gives me 1/2 e to the 4th minus 1/2 e to the 0. I can factor out the 1/2 from each term, so I have 1/2 e to the 4th minus 1, because anything to the 0 power is 1 here. So here I have my final answer. Here I have the integral from 2 to 5 of dx over x, which, remember, is the same as the integral from 2 to 5 of 1 over x dx. So the antiderivative of 1 over x is natural log of the absolute value of x, evaluated from 2 to 5. So we go ahead and substitute in 5, so we have natural log of the absolute value of 5 minus natural log of the absolute value of 2. But we can do some further simplifying here. So first, absolute value of 5, well, that's just 5, and absolute value of 2 is just 2. But our properties of logs say that because I have natural log on each of these with the same base and they're being subtracted, I can turn this into one logarithm of a quotient, natural log of 5 over 2. Now let's look at a different type of example that involves the fundamental theorem of calculus. So let big F prime of x equal little f of x. And we know that the integral from 2 to 7 of little f of x dx is equal to 9. If the antiderivative big F of 7 equals 4, find f of 2. So notice that 2 and 7 are my limits of integration on the definite integral. So here, what we're going to go ahead and do is think about it like this. So the integral from 2 to 7 of f of x dx is equal to 9. What we know about little f of x is that it's equivalent to big F prime of x dx. So this must also be equal to 9. Now, the integral from 2 to 7 of big F prime of x dx is the antiderivative of f prime, which is f, evaluated at 7 and evaluated at 2. So the left side is big F of 7 minus big F of 2. So that must also equal 9. So now I have one of these pieces of information. Big F of 7, the antiderivative at 7, was given as 4. So I can go ahead and substitute in 4 for f of 7, so 4 minus f of 2 is equal to 9 to allow me to solve for f of 2. So over here, if I go ahead and subtract the 4, I get negative f of 2 is equal to 5. So f of 2 is equal to negative 5. So a slightly different application of the Fundamental Theorem of Calculus, Part 2. In this example, the graph of f is shown in the figure. So this is the graph of f of x. if the integral from 1 to 3 of f of x dx equals 2.3. So we'll stop right there. So the integral from 1 to 3 of f of x, this was f of x, so the area under the curve from 1 to 3 is equal to 2.3. So I'm going to highlight that region from 1 to 3, the area under the curve. All of this is equivalent to 2.3. And we're told that big F prime of x is equal to little f of x. Then we're asked to find what is big F of 3 minus big F of 0. So this is different because I have this 0 now involved, but the information I was given was from 1 to 3. So what we want to do is think about big F of 3 minus big F of 0 as its equivalent in a definite integral form. So this quantity would be equivalent to the integral from 0 to 3 of little f of x dx. That's what I'm being asked to find. So big F of 3 minus big F of 0 is the definite integral from 0 to 3 of f of x dx. So now I want all the area from 0 to 3. I only have the area from 1 to 3. But the region that's missing in terms of area is a perfect rectangle. So all I have to do is find the area of that rectangle and add it to the area under this curved part that I was told is 2.3. So in other words, what we're really doing is we're saying this is equivalent to the integral from 0 to 1 of f of x dx plus the integral from 1 to 3 of f of x dx. The integral from 0 to 1 is a base of 1 and a height of 2 for the rectangle, plus 2.3, which was given, for a total of 4.3. So again, another application of the fundamental theorem of calculus. So working backwards, recognizing that this antiderivative evaluated at 3 minus the antiderivative evaluated at 0 is equal to a definite integral with the limits of integration 0 and 3 of the function little f of x. The Fundamental Theorem of Calculus Part 1. We have to begin by defining an area function. So our area function a of x is equal to the integral from little a to x of f of t dt. And this represents the signed area from a to x. So I want us to note that a is a real number and t is what we call a dummy variable. So we don't want to keep the same value here, x, as is the input variable for our area function a of x, because this input value for x is going to become the upper limit of integration here. So we're going to be finding the area from a to different values of x under the function f. So we just really want to think about it as f and assign a w variable, a different variable here to help us understand that this is not the exact same variable that we're substituting into our area function. So this area function starts at some number a on this horizontal axis. So I'm going to go ahead and say this is my value of a. And we're interested in plugging in different values for x. So let's say we substituted in 0. So what that means is that we're going to try to find the area between a and 0, between the curve and the x-axis. So that number is going to be the output of our function. So it's going to be the area of that rectangle. And then we can try to plug in a different number. So we can try to plug in 1. So a of 1 would be the integral from a to 1 under this function that we're calling f. So all the way from a to 1 would be this complete area here, so between the curve and the x-axis. So this is a function because we can plug in different values of x into the upper limit of integration, and if a is fixed, that's going to give us outputs that represent areas under the curve of this function f. Let's continue on with that example. So given the graph of f of x, with a of x equal to the integral from -1, so we have our fixed value of a, to x of f of t dt. So notice we're told this is the graph of f of x, but I'm going to ignore that x part, just label it as f for now, and inside of the area function we're labeling it with a different dummy variable t. So find each of the following. Find a of 0. So a of 0 means we're trying to find the integral from -1 to 0 under the function f, or f of t dt. So here's -1, here's 0. So we are interested in the area between the curve and the x-axis. Now since I'm below the x-axis, my area will be negative, and my width of my rectangle is 1, and the height of my rectangle is 2 units. So I'm going to end up with -2 as the value of a of 0. If I move on to a of 2, I have the integral from -1 to 2 of f of t dt. So we're going to continue and go all the way to the x value 2 over here, and we want the total area from -1 to 2. So we're really just adding on the area of this triangle. Now, the entire answer is going to have to be a negative answer because this is all below the x-axis here. So this triangle here has a base of 2 and a height of 2. So here's what we have. The total answer is negative, and we're going to have 2 plus 1/2 base times height. So the 2 was from the original rectangle, and then 1/2 base times height for the triangle. So we end up with -4 as our answer. And now we can go ahead and try a of 6. So a of 6 is the integral from -1 to 6 of f of t dt. So we already have everything from -1 to 2, so let's go ahead and figure out where we are going to stop now. 3, 4, 5, 6. So we're going to go all the way over here and find all of this area. So we already have that this whole region is -4 and this whole region is going to be positive. So I have -4 plus, now the base of this triangle is 4 units across and the height is 4 units up. So I have 1/2 base times height. So I have -4 plus 8, so I end up with a total area of +4. The next one is asking us to find a of -4. So we have the integral from -1 to -4 of f of t dt. But automatically I should notice that the limits of integration don't go from least to greatest. The bottom should be the smaller number. So if I want to switch that, then I'm going to have negative the integral from -4 to -1 of f of t dt. So I don't want to forget about the fact that I have that negative in the front. So now I'm looking for the area from -4 to -1. So that's going to be a rectangular shape from -4 to -1, and since this is below the x-axis, this is going to be a negative area. So the base of my rectangle is 3 units, 1, 2, 3, and the height is 2. So remember that I have the negative on the outside, but I'm also going to have a negative area. So the base is 3 and the height is 2. So overall, I'm going to have a +6 as my area. Now lastly, I'm asked to evaluate a of -1. So that means the integral from -1 to -1 of f of t dt, which is nice and quick since I'm going from -1 to -1, I'm not going anywhere. So I'm not collecting any area, so my answer is just 0. Accumulation function. Another name for our area function, a of x, the integral from a to x of f of t dt, is an accumulation function because we are constantly accumulating area as we substitute in different values of x. Now, since it's a function, we want to find the derivative of a of x. So in this example, we're going to find a formula first for the area function defined by a of x equals the integral from 3 to x of t squared dt. And then we'll use it to find the derivative and see if we notice anything. So let's go ahead and start with a of x is equal to the integral from 3 to x of t squared dt. So to find a formula for a of x, I'm going to go ahead and apply the Fundamental Theorem of Calculus Part 2 here. I'm going to find the antiderivative for t squared, so that would be t cubed over 3, and evaluate this from 3 to x. And so I'm going to go ahead and substitute in x first and then 3 second. So I'd end up with 1/3 x cubed, and then minus, if I plug in 3 cubed over 3. So I'll go ahead and rewrite that over here. I have a of x is 1/3 x cubed minus 9. So we've actually found an explicit formula for this area function. So 1/3 x cubed minus 9. We were able to do that because we could easily find the antiderivative of this t squared function here. So now we have just a polynomial. To find the derivative, a prime of x, we're going to use the power rule. So we're going to go ahead and bring the power to the front, reduce the power by 1, so we're going to get just x squared. We're just going to get x squared. So we found the derivative, and now we want to see, well, what do we notice? So if we go ahead and take a look at our original area function here, our accumulation function written as a definite integral, if we look at the integrand was t squared. And if we look at attempting to take the derivative of an integral like this, what happened was we ended up getting just x squared out as our answer. So the a of x function, its derivative was simply x squared, which is just the integrand of our accumulation function, but with x substituted in instead of the dummy variable t. So keep that in mind. We have now arrived at the Fundamental Theorem of Calculus Part 1. Let f of x be a continuous function defined on the closed interval from a to b. Then a of x equals the integral from a to x of f of t dt is an antiderivative of f of x. Or another way to think about this is a prime of x is simply equal to f of x. Or another way to think about this, if we take the derivative of this accumulation or area function, the integral from a to x of f of t dt, so the derivative of this definite integral that represents an area function, that's simply f of x. So if you notice what's happening, the upper limit of integration, the variable in our accumulation function, simply replaced the input of the f function, the dummy variable. So the x just goes right ahead and goes into the integrand into the dummy variable. And a has to, of course, be a real number. So let's go ahead and try some of these Fundamental Theorem of Calculus Part 1 problems. So in this example, find the derivative of a of x equals the integral from 4 to x of the square root of 1 plus t cubed dt, and find a prime of 2. So first find a prime of x. So I'm interested in taking the derivative of this area function, this definite integral, where I have x as the upper limit of integration and 4, a constant, as the lower limit of integration. So on this one, we wouldn't be able to find a general antiderivative for this integrand, like we did when it was just t cubed. So here we can apply the Fundamental Theorem Part 1, which simply says the derivative of this integral is replacing the t in the integrand with the variable x. So it's just the square root of 1 plus x cubed. So essentially the idea is that the derivative and the integral are inverse functions, and they basically cancel each other out. So we no longer have an integral because we took the derivative, and the derivative and integral are gone. We just have the integrand, but replacing the dummy variable with the variable x. And now a prime of 2, we have to take the derivative before we can plug in the number, so we're just going to substitute in 2. We get 1 plus 2 cubed, so the square root of 9, which is 3. For further examples, we have find the derivative with respect to x of the integral from 4 to x of sine of t squared dt. So we have this area function of x here. Take the derivative with respect to x. So applying the fundamental theorem part 1, the x simply replaces the dummy variable in the integrand. So we end up with just sine of x squared. So we would not have a dt. We never had dt's on our derivatives, right? Remember, we're taking a derivative. We never had plus c on our derivative, so our answer is simply sine x squared. On this example, we have the derivative with respect to x of the integral from x to 3 of e to the t dt. So our problem here is that we do need the variable to be in the upper limit of integration, and if we switch, then we have to go ahead and pull out a negative. So we're going to have the derivative with respect to x of negative the integral from 3 to x of e to the t dt. But remember that constants, -1, just come down with the function when I'm taking a derivative. So here, when I take the derivative of the integral from 3 to x of e to the t dt, the x replaces the dummy variable t. So I'm going to have e to the x, but with a negative in front. So I have negative e to the x. Now we have the Fundamental Theorem of Calculus Part 1, but with the chain rule. So if I take the derivative with respect to x of the integral from a to a function now, g of x, instead of just x, of f of t dt, I have to apply the chain rule, where now the g of x function does replace the dummy variable inside the integrand. So I do have f of g of x, but now I have to take the derivative of the inside, apply the chain rule, which would be g prime of x. And again, a has to be a real number. So applying this, I have find the derivative with respect to x of the integral from 2 to x squared of the natural log of t dt. So here, again, the derivative with respect to x, I do have an area function here, but instead of x, I have a function of x squared. So the x squared does replace the variable t in the integrand, so I have natural log of x squared, but then I have to multiply by the derivative of the inside. So just the inside, not the derivative of the natural log of x squared, just the derivative of x squared. So that would be times 2x. So we're only taking the derivative of the upper limit of integration, whatever that function is. So this is my answer, 2x times the natural log of x squared. And let's go ahead and take a look at a few more. So find the derivative with respect to x of the integral from -2 to cosine x of sine of t dt. So we're going to go ahead and take the upper limit of integration, the function cosine x, and plug it into the dummy variable of the integrand. So we get sine of cosine x, and then we're going to multiply by the derivative of the inside, so cosine x, the upper limit of integration. So the derivative of cosine x is negative sine x. And there's really no simplifying that we can do here. And this next one, the derivative with respect to x of the integral from x to x cubed of 4 to the t dt. So this one is different because there's no number either in the upper or lower limit of integration. So what we're going to have to do here is we're going to have to think about this problem as split up into two separate integrals. So we're going to go from x to 0 of 4 to the t dt plus the integral from 0 to x cubed of 4 to the t dt. And in all honesty, it doesn't matter what constant you use because the Fundamental Theorem of Calculus, Part 1, doesn't depend at all on the constant value. Whatever that value of a is, it hasn't affected at all what the derivative of the accumulation function is going to be. So here, I just need to split it up at a particular constant. So I'll go with 0. So x to 0 plus 0 to x cubed. And then I'm going to go ahead and flip the limits of integration on this first one. So the derivative with respect to x, the integral negative the integral of 0 to x of 4 to the t dt. And then we're also going to take the derivative with respect to x of the integral from 0 to x cubed of 4 to the t dt. So here, now we have the variable in the upper limit of integration. It's just x, there's no chain rule. So the x just replaces the t, and I keep the negative. So I have negative 4 to the x, and then plus, here I do have to apply the chain rule. X cubed goes into the t, so I am going to have 4 to the x cubed times the derivative of the inside. So the derivative of x cubed, the inside, is 3x squared. So here, we'll go ahead and write our final answer as negative 4 to the x, and I'll put plus 3x squared in front, and then 4 to the x cubed. So now finally, this was called the Fundamental Theorem of Calculus, so that should indicate its importance. And here's the main idea. The FTC Part 2 said that the integral of a derivative gives the original function. So if I have the integral from a to b of f prime of x dx, so the integral of a derivative f prime, that simply gave us f, the original function, evaluated at b, minus f evaluated at a. FTC Part 1 said the derivative of an integral gives the original function. So if I take the derivative with respect to x of an integral where x, or a function of x, is in the upper limit of integration, I end up with just the original function, the integrand, f of x. So derivatives and integrals have this inverse relationship.